And in physics, it's Mr. Neff. Let's just finish up our talk about standing waves on strings. This won't be a real long video. We actually just have one more example to go over, and it's this number 33. And it says we have a string that has a linear density of 8.5, 10 to the minus 3 kilogram per kilogram per meter, and it's under a tension of 280 newtons. It says the string is 1.8 meters long. It's fixed at both ends, vibrating in the standing wave pattern as shown. Now, you can see as well as I can that this is the third harmonic, because I can see 1, 2, 3 antinodes. And so I know that we're dealing with frequency 3. I know we're dealing with wavelength 3, and I know that product will be equal to the wave speed. First, it says, what's the speed? Now, the speed on any string is determined by that equation that has the tension and the linear mass density in it. So, speed on a string, square root of the tension divided by the linear mass density. If you just go ahead and substitute in the tension and the linear mass density there, you will end up with 181.49497 meters per second. Just two significant figures on those numbers, so only the 1 and the 8 are significant there. And B, it says, what's the wavelength? Now, wavelength of the standing wave pattern. And so the standing wave pattern has a wavelength that, well, it's the distance that it takes for one wave shape. That's 2/3 of the full length. And so I'm going to say that wavelength 3 is the length of the string times 2/3. And that's going to be 2/3 of 1.8 meters. And that's going to be 1.2 meters. And then lastly, what's the frequency? Well, as I said earlier, the frequency 3 times wavelength 3, well, that'll be equal to the wave speed. So the frequency 3 will be equal to the wave speed divided by wavelength 3. So if you divide those two numbers we just calculated, the 181 divided by the 1.2, you're going to get 151 hertz with significant figures. And what did the scarecrow say about his job? He said, "My job isn't for everyone, but hey, it's in my genes."